Um, in chapter 4, the first section is going to be about using the inverse trig functions. And this is an extremely important section. This is one that is kind of a foundational skill to like a couple of other chapters. So this is one that we really want to make sure that we are paying attention on, or feel really good and engaged and understand what's going on. And while I don't think that what we're going to be doing in this section is difficult or should be difficult, it is something we have to pay attention to, and it is maybe like a little bit detailed, but the process itself is not like lengthy once we've kind of gotten the handle on it, or need not be lengthy once we're good at it, but takes a little bit of explanation. Okay with that? All right. So the first thing we want to do is we're going to talk about, like, conceptually, what are these inverse trig functions? And I'm going to just kind of talk and do this graphically, as I think this is the most effective way to kind of do this. So I'm just going to kind of talk and draw some pictures here about what's going on. So let's talk about the inverse sine function first. Actually, before I do this, let me say a couple of things first. So recall when I do sine of something, what kind of things do I get to take the sine of? Sine, cosine, tangent, what can I plug into those? Angle measures, yeah. So I have an angle, right? And what comes out is a number. Everybody agree with that? So what sine inverse should be able to do is I should be able to plug that number back in, and out should pop that angle. Everybody agree with that? That's how the inverse function needs to work. So this is going to be helpful to us in solving for angle measures, right? If we need to recover an angle measure that does something, we're going to end up having to use one of these inverse functions to do so. Okay? All right. So let's start with just the graph of regular old sine x. So if you look at the picture here, that's the graph of sine x. When we create an inverse, when you guys did that in Algebra 2, do you remember how you did that? You just swap the x and y coordinates. So each of these points on our function has an x and y. If I just swap the y coordinate with the x coordinate for each point, what I'm going to get is the inverse. That's the blue graph. What do you notice about this blue graph that's potentially a problem? It's on the y-axis. Okay. Why is that a problem, though? That is an observation, for sure. Is that a problem? So you're kind of dancing around what I'm looking for, but you're not quite on it. But you're getting close, which is good. I love that we're trying to take stabs at it and stretch and, are willing to take some risk and be wrong. That's exactly what I'm hoping for. Think all the way back to chapter 1. What did we talk about mostly in chapter 1? Talked about functions, right? Look at that blue graph. Is that a function? No! It's not a function. Why not? Yeah, it fails a vertical line test, which would, in like the y-axis is going through it. That's a vertical line,
Oh, okay.
right? Like you were close to what I was looking for. You just like, I don't know if you were thinking along the same lines that I was hoping you were going to get to. I thought I could nurse you along there, but great. Now, why is that a problem? The fact that this is not a function. What I'd like to do eventually is be able to like program that inverse into my calculator so I can type something and it'll output the angle measure, right? How many angle measures are we outputting for any given number? Infinitely many. Because if you look, if the x's are the angle measures, how many angle measures? And the y, if the x is a number and the y is the angle measure, how many angle measures do I have for any given number? Infinitely many, right? Because this wave just keeps going back and forth as we go up the y-axis. So that's a problem. Okay, everybody agree? So we're gonna have to do something to fix it, to fix this problem. What we're gonna do is we're gonna go back to our graph of sine. And what I want to do is I'm going to cut off some of our sine function so that when we create an inverse, it'll pass a vertical line test. Okay, to do that? So what I want to do is I want to take the longest piece of my sine function where no y coordinates repeat. So if I start at the minimum here at negative 0.5 pi, and I go all the way to the maximum at positive 0.5 pi, no y coordinates repeat in there, correct? And that's the longest segment that I can have that none of the y coordinates repeat. Everybody agree? All the y coordinates get covered. The range of this function goes from negative 1 to positive 1. I cover all of the range with that piece, and I get none of the duplicates. So what I'm going to do is I'm going to chop this at negative 0.5 pi and chop off everything before that, and then slice it again at positive 0.5 pi and cut off everything after that. So that's the green graph. That's all I have left of the original graph of sine x. Everybody okay with that? Now if I take that graph and I swap the x and y coordinates, what I get is that purple part. Notice, does that purple piece pass the vertical line test? Yes. Is that a function? Yes. What's the problem though? Well, the only angles that this purple function can output are those between negative pi over 2 and positive pi over 2. So it can't output any angle, but it is now a function. What this means is if I want to find any angle, the calculator cannot give me the answer on its own. I am going to have to do a little bit of work with this also to get the actual value I desire. Is everybody okay with that idea? All right, so let's just kind of summarize what we did here. So we start off with the graph of y equals sine x. The domain for that is all real numbers, and the range went from negative 1 to positive 1. we then restricted its domain down to just negative pi over 2 to positive pi over 2. So when we created our, actually let me write it this way. When I create my inverse, actually I'm going to call that x instead of y. My domain for the inverse is the range of the original, and the range for my inverse is the domain from the original. And this thing now, that was a function. Everybody's okay with that? We're going to do that 2 more times, one for cosine. And then we're going to do it again for tangent. So for cosine, I get the same problem, right? If I try to invert it immediately, though my inverse function is not going to be my inverse will not be a function. So again, I'm going to restrict the domain, although because the shape of cosine graph is different, the domain I'll restrict it to is going to look a little different. But like whatevs. Pretty okay here. And then my third one is tangent. Oops. Yeah, okay. Wait a minute, what was that? I have to go back and I have to look at this. I don't want to write this down incorrectly. That's what it is, okay. Now remember, the graph of tangent looks different, right? Than sine and cosine. The graph of tangent looked like a bunch of these little like sideways S's. Or like rotated S's. You guys remember that? It kind of looked like this with the asymptotes on either side of it. So we do the same thing. But I have a question for you guys. Notice when I wrote the restricted domain for tangent, I used a parenthesis. But when I wrote the restricted domain for sine, I used brackets. What's the difference between a parenthesis and a bracket when I write an interval like that? Do you guys remember? Way back to chapter 1 when we talked about interval notations.
Wasn't it like, didn't it depend if the number was included?
Excellent. Yeah. Do you remember which one was which?
Was the bracket if it's not included?
It's the other way around. Yeah, so the bracket means that that number is included in the set. The parenthesis means that number is not included. So my question for you, when I look at tangent, why didn't I include the negative pi over 2 and positive pi over 2 when I restricted the domain? Why did I choose that? Why did I write the restricted domain for tangent so that it didn't include negative pi over 2 and positive pi over 2? Well, look at this part right here. Is 1 an odd integer? Sure. So that would be 1 over pi over 2. Or sorry, 1 pi over 2, correct? If I plug 1 in for n. Pi over 2 wasn't in the domain for tangent. So it can't be in the restricted domain for tangent. Everybody agree? What's going on at pi over 2 on the graph? Why isn't that in the domain? It's the location of an asymptote. Guess what negative pi over 2 is? It's also the location of an asymptote. That's why those values in the restricted domain cannot be included. It's because they're not part of the domain of tangent, because that's where the asymptote is. Oh, all right. Yeah, whatever, no big deal. So, Mr. Kulik, we did a lot of seeming like kind of theoretical stuff here. What do I really need to know? Well, this is what you need to remember. For sine, the only angles the calculator can give you are those between negative pi over 2 and positive pi over 2. For cosine, the only angles the calculator can give you are those between 0 and pi. For tan inverse, of x, the only values the calculator can give you are those between negative pi over 2 and positive pi over 2. You need to remember that. Okay? That's like a note card thing that I would put on my note card for this chapter. If you're making a list of things to put on your note card as we go, that would be something I would want to include. So let's just show you guys how to use your calculator to do something like this. Okay. So let's pull up our calculator. The first thing that I need to check before I start doing anything with sine, cosine, or tangent on my calculator, or sine inverse, cosine inverse, tangent inverse on my calculator, is the mode. Whenever you're using sine, cosine, tangent, sine inverse, cosine inverse, or tangent inverse, you have to worry about the mode. Now, for a problem like this, I don't tell you whether I want my answer in degrees or radians. What do you suppose I probably would prefer? radians. Degrees are great if it's like a story problem with some context. For just like a number, like a problem like this, it's like wholly abstract. Probably prefer to be in radians. So I'm going to press the mode button and check to make sure I'm in radian mode. Hey, I wasn't. Let me go down and turn that into radian mode. Once I've done that, I can press second in the mode button to return to the main screen. To get to the inverse functions, I'm going to press the second and then the sine, cosine, or tangent button. So for this first problem, part A, I'll press second. That's the blue button. And then cosine. And then type in negative 0.54. So what that tells me is cosine inverse is 2.14 radians, right? Remember, because what we're getting back is an angle measure. Everybody's okay with that? It's worth pointing out to you as well that what that angle means is if I do cosine of that angle, I better get negative 0.54 back, which is indeed what happens. Right? That's just what it means to be an inverse. Okay, so far? Okie dokie. To the next one. So second, tan negative 7.1. And I get negative 1.43. So far, so good. Try doing the next one on your own. Type that next one in. What happened? You got an error. What kind of error? What did it say when you got the error?
Domain.
Domain. What does that mean? If it tells you you got a domain error. It means that the number that you plugged in is invalid. Go back up top here. Look at this. What's the domain for sine inverse? Negative 1 to 1. What did we plug in? Negative, or we plugged in 1.4. Uh-oh! That's too big, right? So what should I write here? Undefined, because 1.4 is too big. Elise, certainly. Does everybody feel okay so far? Yeah? It's all right? Okay, let's do another set of examples. Notice the directions here. What am I asking for? In the directions? Exact value. in your trigonometry class, if somebody asks for an exact value for an angle or a trig function, what are we going to be using? What's that? Nope, not degrees. Not necessarily. Well, yeah, we're going to give our answer in radians, but like, how are we going to get our answer? What tool are we going to be using? Not the calculator. The unit circle. Yes, when you hear exact value in this class, you should immediately go, I'm probably going to need to use the unit circle to do that. Let's grab a copy of that. Where are we over here? Bloop. All right. So the first thing that I'm going to do is I need to go back and look at the domain for cosine inverse. The domain for cosine inverse is 0 to pi. What quadrants are covered by the standard position angles from 0 to pi? Don't make a face like that. This is not a hard question. Bye, Cheyenne. When I'm drawing a standard position angle, where do I start drawing my angle at? This is a chapter 2 thing. Should still remember how to do this. Start on the positive x-axis. Everybody agree? If we're drawing a positive angle, like 0 to pi, which way do we rotate? Counterclockwise, that's to the left. "90 degrees is the same as pi over 2. All the way here to pi, which is the same as 180 degrees. What quadrants did we cover here? Q1 and Q2. Is everybody okay with that? So, what am I going to do now? I'm going to go to the unit circle. In quadrants 1 and 2, I'm going to be looking for the place where the x-coordinate, because it's cosine on the unit circle, the x-coordinate represents cosine. You guys remember that from chapter 2? Is equal to negative root 2 over 2. So let's go look at our unit circle. So I'm just looking at the x-coordinates in quadrants 1 and 2. There's the one place right there. Everybody agree? So my answer should be 3 pi over 4. And I'm done. Well, that wasn't so bad, Mr. Kulik. So far, so good. Let's look at this tangent inverse one. Again, we'll start with the domain for tangent inverse. Okay. When I start drawing my angles, where do I draw them starting from? Positive x-axis. My positive angles, I rotate to the left. So quadrant 1 is going to cover is covered by 0 to pi over 2. To do negative angles, which way do I rotate? Clockwise or to the right. So there I'm covering quadrants 1 and 4. Is everybody okay with that? So now I'm going to go to the unit circle. I'm going to look in quadrants 1 and 4. And I remember that on the unit circle, tangent is y over x. Everybody's okay with that? So what I'm really going to be looking for is a place where the y coordinate has a square root of 3 in it, and the x coordinate has a regular 3 in it. Is everybody okay with that? Let's go look. Mr. Kulik, everywhere I look on the unit circle, no matter where I look, I don't see any regular 3s in any of the coordinates. Do you guys see any regular 3s? Oh, okay, so this one just can't be done with the unit circle. That must be it, right? Wrong. So here's the trick, and it's a sneaky one. I'm going to think about that regular 3 in the bottom as the square root of 3 squared. Right? That's still the same thing as regular 3. That will allow me to reduce and write it as 1 over the square root of 3. So what I'm going to do is I'm going to look for the place where the y coordinate has a 1 in it and the x coordinate has a square root 3 in it. Oh, great. Okay. That I see. The y coordinate has a 1 in it. The x coordinate has a square root of 3 in it. You guys agree with that? So my answer is pi over 6.
No.
Elise.
So you got different quadrant 1.
Mm-hmm.
Could you find the quadrant where the y has a 1 and the x has a square root?
I can find a place where the y has a negative 1 and the x has a positive square root 3, or a place where the y has a negative or has a positive 1 and the x has a negative square root 3, but I can't find one where they're both positive. Right? Like if I went down, if I go down here, I could try this, but look, negative. So, cool? Good question, though. All right. One more example. Is this starting to feel okay? It's not bad, right? Very light on calculation, but there's a lot of detail going on here about figuring out where to look and what to look for, right? But the actual mathematics, like the number crunching that we're doing, the calculation that we're doing, it's not so bad. Just move that out of the way a little bit. Okay, so for sine inverse, We'll start with the domain. Oh, Mr. Kulik, look at this. Isn't this almost the same domain as B? Everybody agree? So the quadrant's still going to be the same. 1 and 4. I don't really even need to draw another picture. Okay, so I'm going to go to the unit circle. I'm going to look in quadrants 1 and 4 for the place where sine, what is sine on the unit circle? It's y. If you don't remember that sine is y, cosine is x, and tangent is y over x, those would be good things to go into your note card if you're kind of keeping track of note card things as we're going. Okay, so let's go to the unit circle looking for where y is equal to negative 1/2 in quadrants 1 and 4. There it is. So 11 pi over 6. Everybody happy with that? Here's the problem. That answer's wrong. Wait. What? We did the exact same thing as before. Why is that answer wrong, Mr. Kulik? I don't think it's wrong. We did exactly the right thing. Okay. I understand your frustration. Look at the domain. My answers have to be between negative pi over 2 and positive pi over 2. Is 11 pi over 6 in between those two values? No. However, this is almost the right answer because it is giving me 11 pi over 6. If I take the sine of that, I do get negative 1/2. So what am I going to do to this angle? I'm going to find an angle that's coterminal to this. Remember that phrase from chapter 2? How do we find an angle that's coterminal? We add or subtract 2 pi or 360, depending on whether we're working with radians or degrees. What are we working with here? Radians. Okay, so we should be using 2 pi. Now, I need to decide whether I should add or subtract. We should subtract because 11 pi over 6 is too big. Okay? Now I'm going to notice to subtract fractions, I need to make a common denominator. So I'm going to think about 2 pi is just 2 pi over 1. To make a common denominator, I'll multiply 2 pi over 1 by 6 over 6. So I get 11 pi over 6 minus 12 pi over 6, which is negative pi over 6. And that is in between negative pi over 2 and positive pi over 2. Right? Negative 1/6 is bigger than negative 1/2. Right? Negative, or 1/6 is about 1.6. Or 0.16, excuse me. Sheepers creepers. So negative 0.5 is definitely smaller than negative 0.16. And obviously that's smaller than or negative 0.16 is smaller than a positive. So like we're good. We're in between. Everybody okay with that? So this little step here, if we were finding something in quadrant 4, when we went to the unit circle and the angle we pulled came from quadrant 4, we're going to have to remember to do that every time. Is everybody okay with that? Alternatively, if you don't like the coterminal idea, you could just go, okay, I'm just going that way, right? If this is 2 pi over here and this is 11 pi over 6, I must have gone 1/6 of a pi that way. And because we're rotating clockwise, it has to be negative. And you could just kind of look at the picture and come up with that value. Either is okay. I think for most of us, the way we did it the first time is probably the easier way to do it, because it's like the same way every time. I don't have to think. But if you're like, yeah, I don't like writing stuff down, if I can just look at the picture and see it, let me just do that. Either way is fine, though. Everybody's okay here? So far, so good? All right. One more set of examples, and we're going to call this good for today. Let's actually do that. Oops. Okay, here it says find the exact value on the given interval. So this is almost the same direction as the previous problem. What's additional though? It says on the given interval. So in each of these cases, we've given you an interval, right? How does this change the process that we've just done? We still do everything the same way until we get our answer from the unit circle, and then we're just knowing that we're going to have to add or subtract some 2 pi's until we get our angle to fall into where we need it. Everybody cool? All right. So here, I'm actually going to do something a little bit different to figure out where we're going to be looking. So theta equals cosine inverse of negative root 3 over 2. This is the same thing as cosine theta equals negative root 3 over 2. Everybody's okay with that? On the unit circle, cosine is the same as x where, in what quadrants is the x coordinate negative? Those ones, right? Quadrants 2 and quadrants 3. Everybody agree with that? Now, if I look at 5 pi over 2 to 7 pi over 2, these are positive angles. So when I start at the positive x-axis, I'm going to be rotating counterclockwise. Half a pi, 1 pi, 1.5, 2 pi, 2.5, 3, 3.5. Oh, boogers. I messed this up, huh? Hold on, Mr. Gulick's changing the problem. Bloop, bloop. Well, I made a mistake. It's hard to do these on the fly sometimes. Let's say from 3 pi to 4 pi. I wonder if I've screwed all these up now. So now we're at 3 to 3.5, 3.5 to 4. Matt? Certainly. So where does my answer, where do I need to look on the unit circle to get my answer? Which quadrant?
4.
Has to be quadrant 3 because that's the only one that satisfies both pieces. From the inverse function, I could land in quadrants 2 and 3. From the interval, I could land in quadrants 3 or 4. Well, then it has to be in quadrant 3. So I'm going to go to the unit circle. I'm going to look in quadrant 3. And I'm looking for where x is equal to negative square root 3. To show you where 3 pi started, right? The part from 3 pi to 4 pi is the squiggly part. Everybody okay with that? So that's 1 1/6 pi, right? 7/6 is 1 1/6. Is 1 1/6 between 3 and 4? Well, no, Mr. Kulik. 1 1/6 is definitely not between 3 and 4. Okay. Is it too big or too small? Too small. So I should be adding 2 pi to that. If I add 2 pi to that, I have 1 1/6 plus 2. That will give me 3 1/6. Is that between 3 and 4? Yes. So all I need to do is add those fractions. Right? 2 pi is the same thing as 12 pi over 6. So 19 pi over 6 should be my answer. Is everybody okay with that? So here we can be a little bit more specific in our search, right? We can explicitly figure out which quadrant we need to find our answer in. Let's go ahead and do this again. So theta equals tan inverse of 1 is the same thing as tangent theta is equal to 1. Tangent is y over x. So I have y over x is equal to 1. If I multiply both sides by x, that's just the same thing as saying we're looking for the place where the x and y coordinates are the same. What are the only two quadrants that can happen in? Quadrant 1, where both the x and y are positive, or quadrant 3, where both the x and y's are negative. Now let's look at the interval. So this time our angles are negative. Which way do we rotate? Clockwise. So negative a half, negative 1, negative 1.5, negative 2, 2, negative 2.5, negative 3, negative 3.5, negative 4, negative 4.5, to negative 5. So we went through quadrants 4 and quadrants 3. Where is our answer at? Where do we need to be looking? Quadrant 3. So we'll go to the unit circle. We're going to look in quadrant 3, where x is equal to y. Where does that happen? Right here, at 5 pi over 4. Everybody okay there? Is 5 pi over 4 is 1 1/4 pi, correct? Everybody agree with that? Is 1 1/4 between negative 5 and negative 4? No, Mr. Gulak, clearly not. It's not even a negative number. Come on. Okay. Is it too big or too small? Too big. So we should be subtracting. Okay. So 1 1/4 minus 2 gives me negative 3/4. Is that in between negative 4 and negative 5? Negative 0.75? No. So we'll do it again. Now we get negative 2.75. Is that in between negative 5 and negative 4? No. So we do it again. That gives us negative 4.75. Is that in between negative 5 and negative 4? It is. So how many 2 pi's did we have to subtract? We did that 3 times. So that's 6 pi, which is really, if I make a common denominator, 24 pi over 6. So 5 pi minus 24 pi over 6 is 19 pi over 4. That's what we're looking for. Is that okay there? I know the fractions are hard for us. I'm trying to make it as easy as I can by turning them into mixed numbers so it's a little bit more tolerable. Notice that when I'm doing this, am I including the pi really when I'm thinking about this? Not really, right? The pi is just getting in the way. I just think about the number part. Can you do that? Yeah. Yeah, you should. All right. Last one here. Oops. So we're looking for where sine is 0. Oh. Well, on the unit circle, sine is y. So where is y equals 0? Not in a quadrant, right? This is on the x-axis. Okay. Notice here that at 0 and at pi, we have answers. Everybody agree with that? This one is between quadrants 1 and 4. This one is between quadrants 2 and quadrants 3. Everybody okay with that? All right, well, let's look at our interval then. These are positive, so I'm going to be going counterclockwise. Half, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, that's 11 over 2. 6, 6.5, that's 13. So we are at quadrants 1 and 4. So we want theta equals 0. Is 0 between 5.5 pi and 6.5 pi? No, definitely not, Mr. Kulik. Okay, how many sets of 2 pi do I need to add to get it between those? 3. 0 plus 2 pi is 2 pi, plus 2 pi again is 4 pi, plus 2 pi again is 6 pi. And that's between 5.5 and 6. Oh, neat. Why was that one felt so much easier? Why did that go quicker? Because we had a quadrantal angle here. We had an angle that actually fell on the boundary between the two quadrants. That's why. So if that happens, it just makes it a little bit faster. Plus, they're usually easy to add and subtract 2 pi's from, because they're usually a whole number of pi or a half number of pi. So it's like the arithmetic's a little easier then for us. Okay, this is where we're stopping. We still have several topics left to do in this section, but this felt like enough for today. From the problem set, you guys should be able to do 1 through 6, and you should be able to do worksheet 1. And there's, one little piece of vocab thing that I need to mention. So there's an alternate notation for these inverse trig functions. So if you see the prefix ARC, the word arc, that's just the same thing as the inverse. It's just another notation. Is that okay, guys? So you'll see that in the homework or whatever. That prefix ARC is the same thing as like arc sine is the same as sine inverse. Is that okay? Not a big deal? Mr. Kulik, why do we have all these different stupid notations? I don't know how many different words do we have for good. And here you claim belly aching about the amount of vocabulary we have in the English language. It's the same idea, like there's more than one way to say something. There's more than one way to symbolize something. The real answer is that all this notation had been developed like many hundreds of years ago in very different parts of the world. And these different parts of the world, when they figured out that this other part of the world is writing it differently than us, didn't want to change. So we're just stuck inheriting all these different notations from different regions of the world. Because in the 1600s, you couldn't really read what Russian mathematicians were doing unless you got Russian math journals and then could actually read Russian. So that was kind of a bit of a hindrance in communication, let alone if you had Chinese access to Chinese work, even more rare that you're going to have somebody speaking Chinese or getting the material from China, So yeah, you have a lot of these inherited weird or overlapping notations that mean the same thing. That's where we're stopping today.